All right, welcome back to 353, 9 a.m. Is there an exam today or something, or midterm?
Several, yeah.
Sorry?
Several, I think multiple classes have.
All right, multiple midterm today. So yeah, it's like another snow day. Could have done this online. I could have not woken up at 4 a.m. That would have been great. All right, well, that's unfortunate because we're back to regularly scheduled lecturing where things are now going to get difficult. So we get to talk about locks today. We're arguing about concurrency. We're arguing about threads. Just as a little reminder, what we had before. Before we had 8 threads. Remember this example from way back when? We had 8 threads all incrementing the same global variable 10,000 times. We ran it, and well, we argued that, hey, the actual answer should be 80,000 if we have 8 threads, each incrementing a variable 10,000 times. But when we ran it, we saw that, it got inconsistent results, and now we get to explain why and fix it properly, or for some depth, or at least have another way to fix it. So what actually happened was something called a data race, and it occurs when sharing data because we were sharing modifications to that global variable across multiple threads. So a data race is when 2 concurrent actions, note here, not even parallel, 2 concurrent, so this even happened with a single CPU. So this definition, also very important, you'll have this seared into your brain. So a data race is when 2 concurrent actions access the same variable, and at least one of them contains a write operation. And that is the case you might have a data race. If both concurrent actions are both reading it, they're both reading the same data over and over again, it doesn't really matter. We'll only have a problem when one of them tries to write it. And in which case we might get some stale data is basically what it comes down to. And we'll see a whole bunch of examples today and why that happened. So to begin talking about it and talking about how to do it properly, we have to talk about atomic operations. So atomic operations aren't fun physics, anything like that. They are just operations that are indivisible. So they either happen or they don't. There's no in between. So you just assume any atomic instruction happens all at once, means you cannot preempt it. You can't do anything concurrent. You can't switch from it. It either happens or it doesn't. But between two atomic instructions, you may be preempted. So you may switch which thread is currently executing. And this makes arguing about our programs hard, especially with higher level languages where one line of C, even though C is not really that high level, translates into multiple atomic instructions. So if you're interested in compilers at all, compilers don't take your C code and spit out assembly. They use something called an intermediate representation, which is kind of like between C and assembly. And it generates assembly from that and does all of its analysis and everything on kind of like a simplified version of assembly. So typically, it's in the format called a 3-address code, or TAC. And this is what is used by compilers for their analysis and optimization. If you ever get interested in that and how software works, compiler courses are a great course to take. That's what started me doing grad school because I liked my compiler course so much. I continued doing it until I got stuck in the academic vortex, and now I am here forever, hopefully, maybe. So 3-address code, again, mostly used for analysis and optimization internally by compilers. The statements are kind of simplified. They represent one fundamental operation. For the purposes of this course, we'll assume each of the operations are atomic. And it's useful to have our code represented this way because it's easier to read than assembly, and we can reason about data races and what's actually going on. So statements are simplified. This is as complicated as a single 3-address code statement gets. A result equals an operand with an operator and an operand, and that is as complicated as it gets. It could be, of course, as simple as a result equals an operand or something like that. So The 3-address code used by GCC is called GIMPL. Don't ask me why it has a stupid name. Something intermediate, something, something, programming language, something, who knows. So to see that, whenever you're compiling, you can use this flag that's fdump GIMPL tree to see that I'm not lying and that that is the name. And to see all the 3-address code generated by GCC, you can use fdump tree all and see all of the GIMPL. So again, easier to reason about your code than low level, than just like trying to reason about the assembly, and it's more general too. So you might see, we're just going to look at briefly, you might care about this more once you get into like programming for performance, or again, a compiler course. So instead of count, the compiler just reasons about the pointer to count, so which is a global, so it just picks that virtual address for it. So if we took ++ count and generated the GIMPL for it, just renaming the pointer to count as just pcount, the GIMPL is the following. We'll see 3 instructions. So the first one is going to be that memory load. So it will load, it'll dereference pcount, get the value of count, load it into a temporary. In this case, for 3-address code, there is not the concept of registers. Well, there's kind of the concept of registers, so they're just called temporaries, but you assume you have an infinite amount of them, and each instruction generates its own unique register, and so we don't have to worry about register allocation or anything like that. So this reads the value of count into a register called D1, if you want to think of it that way, and then that's it. That's the atomic instruction. Then the next is the increment on the value in that register, if you want to think about it that way. So creates a new temporary called D2, which is equal to D1 plus 1. And then it does the write. So it writes the updated value to count, overwrites that value there. So if we go ahead and assume that 2 threads can execute this code concurrently. So again, we're just worrying about concurrency between the 2 threads. So between any of these instructions, we could swap between the other. So in the happy case where it kind of expects how we want it to, we have this value in memory somewhere called count is currently equal to 0. And when we start executing, we only execute, we only have, assume we only have one CPU that can only execute one instruction at a time. So first we start off in thread 1. We execute this instruction. So that loads the value of count into a temporary called D1. So in this case, it would load that value 0. Then next, we take that value, we add 1 to it, put it in a temporary called D2. So that value would just be 1. And then we do the memory write here. So we write the value now 1 to count, and we are now updating count from 0 to 1. Then we context switch over to thread 2, start executing thread 2's code, and then we read the value of count into thread 2's register. So in this case, we would read the value 1. Then we would go ahead, do the increment. So we increment 1 to 2, and then we write out, then we do the memory write with the value 2. So that would update count from a 1 to a 2. And then that gets us our right result. Now, if we rewind, that's only one combination. So for arguing about all of these, we assume each of these instructions are atomic, but we don't know, between any 2 atomic instructions, I can either switch to the other thread or I could stay at the current thread. Each thread individually will run its instructions in order. We can assume that from top to bottom, although that's not really true on modern CPUs either, but I will save you that headache. So just assume each thread runs all of its instructions in order, but we don't know any ordering between the 2 threads. So in this case, if we just think about for this simple example, how many different ways are there to combine these 2 threads? So I can start with this instruction, and then the next thing I could execute could be thread 1's next instruction, or thread 2's first instruction, right? And then after that, I could continue with thread 1, or thread 2, sorry, or switch back to thread 1. You can see how this explodes quite quickly. The exponential number of combinations here we have to worry about. And in order to argue that your software is correct, you have to argue about every single one of these. So that is what makes programming fun and why concurrency issues have lived in the Linux kernel as bugs for, I don't know, like 13 years, something like that. It took 13 years for some people to find some of these bugs. So, for example, most of the time, maybe count is 2, and that's great. But I might get a bad ordering of threads. So bad ordering of threads, again, would be, okay, let's first start executing thread 1. It would read that value of count into its temporary D1. And then we could context switch to thread 2. Then thread 2 would do its memory load. And the current value of count is 0, so it would load that value 0. Now, at this point, we're kind of screwed. It doesn't matter if we switch back to thread 1 or continue executing thread 2. At the end of the day, we're going to get the wrong answer here. So let's just assume we go back to thread 1. If we go back to thread 1, it will take its current D1, which is its own temporary value. Again, that is unique to a thread, and it would add 1 to it. So 0 would get added to 1. Give us the result 1. Then the next instruction it could execute is updating the count, the value of count, to be whatever its current value is in its register, which is now 1. And then we could switch back to thread 2. Now thread 2, well, in its D1 register, its current value is 0, so it would get updated to a 1. And then it would go ahead, execute its next instruction, which is to write the value 1 to count. So it would update it from 1 to a 1, and now we have the wrong answer. So any questions about that? Lots of fun, huh? All right, so again, to analyze data races, you have to assume all preemptions are possible. So the ones that are important for data races, you argue about reads and writes to a location. In this case, I don't really care about the increment or anything like that because that's internal, independent on each thread. What I care about is count. So I'm doing this analysis just on count, and the things that I care about are the reads and the writes. So let's call the read and write from thread 1 as R1, so that's a read from thread 1, and write 1, so that's a write from thread 1, and of course R2 and W2 from thread 2. So if I've, again, assuming no reordering instructions, between threads I always have to have a read and then a write. So all our possible orderings in this case is if I start with a read 1, the next instruction could I could continue with thread 1 and make it to the right, or I could switch to thread 2 and then do the read. And then, well, if I do the write on thread 1, I only have one choice. I have to context switch to thread 2, and then the next instruction would be a write to thread 2, in which case if I did that, that's the happy case where the final value of count is 2. Otherwise, if I switch to thread 2 and do a read 2, then I might switch back to thread 1 and do a write and then do thread 2's write, or I might continue doing thread 2's write and then thread 1's write. Either case, the final answer is a 1 when it should be a 2. And then similarly for the other 3 are the same idea, just thread 2 executed first. But otherwise, it's pretty much the exact same. So these are all of our combinations, and if at least one of them has the wrong output, then we have a bug in our program. So everyone understand this? Cool. So in order to solve this or prevent this, well, arguing about different interleavings between threads is really hard, so we use some construct in order to prevent any switching between threads, and we call them a mutex. So a mutex is short for mutual exclusion, means only one can happen at a time. So they're actually part of the pthread library, and you can create them either statically as a global variable or dynamically. So if you do them statically, you can declare a global called pthread mutex underscore t. That's the type for them. Give it a very, very creative name like M1, and to initialize it, you just set equal to pthread initializer, which is some horrible C macro shenanigans, but it works. If you have some pthread mutex M2 that you declare, I don't know, on the stack or main stack or through malloc or something like that, then you have to call pthread init on it, give it the address of the thing to initialize, and then it has a bunch of attributes, but for this course, we'll just set it to null and get all the default mutexes. And then when you're done with it, like init is like malloc, and destroy is like free. So you have to destroy it once you're done with it. If you want to include attributes, you have to use the dynamic version. The static one will just give you all the default things, which is probably good enough for us for now. So how it works is that mutex type, it's kind of like a lock and kind of like a padlock, if you will. So everything within the lock and unlock is a critical section. So you can think of the mutex itself as a padlock, and then there's only one key around that's hanging on the wall beside it. And if you lock it, that means you take the key down from the wall, you lock it, and you put the padlock on the inside, and no one else can get in. So you have your code running, then you call lock. After that lock call, you are the only thread that can obtain that lock. There is only one single instance of this mutex, and then you are the only one with exclusive access to run this protected code. Because if some other thread tried to do this lock call, what will happen is, oh, someone already has the lock, I can't proceed, and you'll get blocked until the thread with the lock eventually calls this unlock function. So you are guaranteed between the lock and the unlock call that only one thread can be executing this code at any given time. And then after you unlock it, then more code can happen, and then, well, that more code could get preempted, switch to another thread, but everything we want to prevent data races for, any code we need to protect, should go between this lock and unlock call. So we call that protected code. You might call it a critical section. Has lots of different names depending on it. We're going to have a case where there's potential to have a deadlock if you're using multiple mutexes, which we'll get into later. For now, we'll just worry about a single mutex. If you have multiple mutexes, though, there's also a function called pthread try lock, and that will just try the lock and not block until you can actually lock the thing. So it will just return, it's like the non-blocking version that will return whether or not you have acquired the lock, yes or no. So if we go back to our code now, if we wanted to prevent a data race, so what we argued about is we had a data race on counter. So because we have 8 threads, they're all running at the same time, all running concurrently, in this case also in parallel, because I have lots of cores on my machine. But again, for data races, all we care about is concurrency. So for this, we've identified that this is the line that has the potential data race. Everything else there is unique to a thread. It's living on that thread stack. So this is the thing I need to protect. So since I need to protect that, well, one way I could protect it and make sure that only one thread is doing this ++ counter at a time is I can go ahead, create a mutex. So again, it's pthread mutex underscore t. I can give a very creative name like mutex, and then just use the initializer. So this will go ahead and initialize it for me. And then if I want to protect the ++ count, I can do pthread mutex lock, give it the address of mutex, and then when I'm done with it, I can go ahead and unlock it. So now, because of that, only one thread can be executing this plus plus counter at a time. So between the memory read and the memory write, I'm essentially preventing any concurrent or any preemptions or anything like that while I'm trying to execute this code. So I could get preempted in the middle of doing this, but if I get preempted to another thread and they try to do the exact same thing, well, they'll be blocked by this lock call because I got preempted while I had the lock, so I locked myself in that room. No one else can come in. So even if they try, we're good. So if I just do that, save it, and compile that, and now I run it, I get 80,000 every single time. It's all nice and consistent. Drawback is, well, I essentially made this serial as well, so it's actually going to be slower than just having one program that just iterates 80,000 times, because again, this is kind of a silly example, but on real programs, this would be like not very much of the work, and this would probably, like the code around this is most of the work. So in real programs, it would only be advantageous to do this if it actually speeds up your program. So in this course, we're just worried about doing things correctly. We'll worry about performance a little bit-ish during the lab, but not very much. Yeah?
Yeah, so if the lock prevents preemption, would it still be possible for multiple threads to be running at the same time on multiple cores?
So the lock doesn't prevent preemption. It just prevents preemption, like the thread currently executing this from being preempted by another thread that is also going to execute that. So let's say thread 1 in the middle of this does a memory read to counter, and then we get preempted and we go to thread 2. Well, in order for thread 2 to execute that plus plus counter, it has to have this lock. So if thread 1 is currently doing it, it means it has the lock, and if thread 2 starts executing and it tries to do that, it would have to get by this lock call, and if it's implemented correctly, it will not be able to, what we say, acquire the mutex, so it can't make it into that code. So it can't do it. But thread 2 could be doing other things. In this case, thread 2 would try, get the lock, see that it can't make any progress, and then hopefully my operating system's smart enough to be like, okay, I'll just go ahead and switch back to whoever has that lock so that we can actually make some progress. All right, any other questions before we attempt to implement a lock? That will make it more fun. All right, so that is just a little preview. Again, we will get into how to actually implement this. So the critical section, again, means only one thread executes that critical section at a time, just like was brought up. Other threads could be executing other instructions at the same time. We still have preemptions. Preemptions still happen. It's just that we can't, no one else can make progress in that critical section if we get preempted and some other thread starts executing. It won't be able to enter that critical section, so we're not going to get interrupted in the middle of doing anything. So if we want to implement a mutex, we need the following properties. We need safety, aka mutual exclusion. So the rule is there should only be a single thread in that critical section at once. That means we don't have to argue about any preemptions happening within that critical section. We know that there won't be a data race there. We also need to have liveness, aka progress. So if multiple threads reach that critical section, one must proceed. The critical section can't depend on outside threads. If you do that, you can mess up in deadlock where threads don't make any progress. Again, we'll see that in the next lecture. And then you might also need bounded waiting, aka starvation free. You can see this also came up in scheduling as well. Operating systems typically do not like having starvation as something that is possible to happen. So what that means in this case is a waiting thread must eventually proceed. It can't be stuck there forever waiting to acquire that lock. All right, so practically, if you were to use threads and you want things to go actually fast instead of slowing down, Your critical sections need to have minimal overhead. You need them to be efficient. You don't want to consume resources while waiting. You want it to be fair, so you want each thread to wait approximately the same amount of time, and they should be simple, so they should be easy to use, hard to misuse. That's generally the design for any kind of library. So similar to libraries, you want layers of synchronization. So at the bottom, we have, at the bottom, we have the hardware provided. We have the hardware provided low-level atomic operations, so like the memory reads and the writes, like the actual instructions they have. And then on top of those, and some other atomic operations, which we'll get into later, you build your high-level synchronization primitives. So for example, a mutex would be an example of one of these. And then using the mutex, you write a properly synchronized application without any data races that behaves consistently and fast. So, So to actually implement a lock and implement critical sections, this has gotten harder over time. Assuming you have a processor with a single core on it, so a uniprocessor system, back in the day, your implementation could be really, really easy. If you have a single core where the only source of preemptions are interrupts, well, then the easiest solution is to just disable interrupts, that's disabling preemptions, and then you're guaranteed that no one will interrupt you. So back in the day, your implementation for mutex lock could just be disable interrupts. Now no one else can interrupt you. And then the unlock would just be to re-enable interrupts again. So this would essentially disable concurrency, assuming it ignores signals and interrupts. But this isn't going to work on multiprocessors where things could be happening in parallel. So our life has gotten a lot more challenging. So we can try to implement this ourselves. So let's look at this. So we will have a lock. We're just going to model it by just an integer, and we're going to assign some magic values to it with some meaning, such that the value 0 means the mutex is currently unlocked, and the value 1 currently means it is locked. So the idea here is that if someone creates one of these locks that we're going to try, they just create an int somewhere, and then we go ahead, they would call init, and then whenever they want to use it, it would be lock and unlock. So somewhere, let's say they tried to use it and gave it the name lock as a global variable. As part of our init, it would be equal to 0. So even arguing about the, well, let's kind of argue about it a bit. So the idea here is that in the lock call, what the lock call does is it has this while loop. So while dereference L is equal to 1, so that means that this will be true when that current value of the lock is equal to 1. So currently, if no thread has a lock, then the current value is 0, so this will be false. And note there's a semicolon here, such that if this was true, it would just be an infinite while loop. It would just go back and forth, back and forth, back and forth until that condition changed. So in this case, the value of the lock is 0, so this would be false, so we would fall out, and then we would change the value of the lock from a 0 to a 1. So that would be what happens when the first thread executes it. So we would say, hey, we have thread 1, and we could say it has the lock, because it's the thread that changed the value from a 0 to a 1. And now the property we should have is that if thread 2 comes along and calls lock, well, then thread 2 can't make any progress, right? So thread 2, if it called lock, the current value is 1, so 1 is equal to 1. So it would just loop over and over and over here until eventually the operating system switches to thread 1. Thread 1 finishes its critical section and then eventually calls unlock, which would change that value from 1 back to 0. And now if we go back to thread 2. Thread 2 could go ahead, oh, well now the current value is 0, so this is false. So thread 2 could go ahead and change that value from a 0 to a 1, and now thread 2 has the lock. And no one else can make any progress. So everyone kind of get the logic for that? All right, so I will give you a minute to think about this. So what happens is, in order to be safe, even if two threads start off by calling this lock function, only one of them should be able to progress. Right? If this is implemented correctly, only one of them will be able to make it past this, no matter what preemptions they have between each other. So I'll give you a minute or two to think about this. Let's assume if thread 1 and thread 2 call this lock function, is it possible that both thread 1 and thread 2 return from this lock function, which would make our mutex essentially worthless? So think about, well, given the current value of the lock and what this code actually does, is there any concurrent accesses or execution of this code that will lead both threads to actually return from it, which would be very, 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 very bad. So I will give you 2 minutes to think about that, and then we will go through it. Oops. All right, any stabs at bad that can happen? Yeah.
I mean, I thought that since either thread can just call init, so then if it calls init and then calls lock, and the second one calls init to reset the
So just two threads calling lock.
Yeah.
Yeah. We're just worried about, we don't really care about init for right now. Yeah.
So they could both read the value of L first, and then both evaluate false.
Yeah, so first step is, well, skipping, well, kind of load. They both read that value of L first, which in more, I don't know, explicit terms means, well, this read right here, this is a memory read, and that's an atomic instruction. So a bad thing that could happen is that thread 1 executes first. It reads that current value into its register. So it would do something like this version of the Jimple, which is the memory read. So it would read that value 0. Then a bad thing that could happen is we could context switch to thread 2. Thread 2 would then go ahead and do the same thing, where it reads the value 0 as well, right? So it's not both happening at the same time. We're just arguing about concurrency, or concurrently. So we actually do have a context switch between them. But now they both read that value 0, and now we're essentially screwed, right? So now it doesn't matter what executes next. If we executed thread 2 next, it would compare D1 to 1, which is true, because which is false. Apparently I got mixed up. So it would compare 0 to 1, that's false. So we would break out of the while loop. It would go ahead and then do the instruction where we update the value of L to be equal to just 1. So we would update the value of the lock to be equal to 1, and we would be able to return from the lock. So now that thread is done writing that lock code. Now we could switch back to thread 1. If we switch back to thread 1, it will do the comparison again. Well, with D1 that it loaded from memory, which is currently 0, which, as you can see, data races are basically caused by using stale data. That's not really true anymore. So it still has the old value 0, but the current value is 1, but we're ignoring it because we already read it from memory, and we're not aware of the other thread. So when we compare, we'll get the value 0, which is false, and then it will go ahead, execute the next instruction, which is the memory write, updating that value from a 1 to a 1. And now both threads would make it by the lock call, rendering our lock completely useless. So everyone get that? Cool. So there's actually 2 issues with this implementation. One, it's not safe, so both threads could be in the critical section, rendering this thing completely useless. And it's also not efficient because it wastes CPU cycles. So it's not intelligent at all. If it worked properly and thread 1 acquired the lock and then thread 2 called the lock function, it will essentially be stuck in that infinite loop until it won't give up the CPU, even though it can't make any progress. It's just going to try and try and try and try and try again. And that's something we just call a busy wait. It's waiting, doing work when it shouldn't really be doing it. It's just going to load that value 1 over and over and over and over and over and over and over again until eventually thread 1 calls the unlock function. So, any other questions for today? Next lecture, we will actually implement this correctly. And it will be a load of joy, but we won't have enough time to do it today. So we get to end a bit early. You get to enjoy the rest of your early morning and go grab a coffee or something like that. So with that, just remember, pulling for you, we're all in this together.